a terceira parte do mini curso do professor Campuzano, e na sequência teremos a sessão dos cursos.
So I will finish today with a short talk. So I told you about first day about how photo emission works. Second day about heavy fermions, superconductors, high temperature superconductors. And today I will tell you about our work that we're doing with the collaborators from Campinas. And Priscilla's here from Campinas, and you can talk to her in Portuguese about these experiments. She knows more than I do. So why are the heavy fermions interesting from the physics point of view? If you think about the specific heat, which measures how heavy the electrons are, the formula usually has the mass of the electron and it has the density of electrons. So you can measure the specific heat and estimate the mass of the electrons. And what happens in a regular metal, like aluminum, lanthanum aluminate, the specific heat is very small because the mass of the electron is just one electron mass. If in this material I exchange lanthanum for cerium, it's the same structure. Look at the specific heat is hundreds of times higher. And effectively, it means that the electron mass has become very, very heavy. So this is the specific heat of the material that we're going to study. And this is at higher temperature, it's small, and as you reduce the temperature, it's constant as a regular metal, more or less constant, but then it increases dramatically. And why does it increase? But if you integrate this and you find out that the effective mass of the electrons in this material is 400 times the free electron mass. So it's really an unusual situation compared to a regular metal. So what this means, which is even more important, is what almost never happens in condensed matter physics, that the strength of the interaction increases with decreasing temperature. So the interaction gets stronger and stronger and stronger. In fact, it gets so strong that you cannot use perturbation theory. We cannot use many of the methods that we use now. The problem is very similar to quark confinement. You know, in quarks, the interaction is so strong that you cannot pull them apart. So when you get to the peak here, it's like that. You cannot describe it using the methods that we know normally. So why is this happening? Suppose I have, these materials have p electrons, d electrons, and they have things like cerium, which have f electrons. And it's the f electrons that are doing this strange phenomenon. So if I take conduction electron and f electron, okay, and I look at it at high temperature, then I find that, well, what happens is that the electron just scatters a little bit from the f electron. It almost doesn't notice. The f electron is just an isolated spin. Okay, it's a magnetic moment, and it's just sitting there. It's split off from the main conduction electrons. So the specific heat at high temperatures is low. The effective mass is low. As I lower the temperature, then a resonance starts to appear between the conduction electron and the F level. They start to interact more and more, and this interaction gets stronger and stronger, and at very low temperatures, the F level is stressed by a lot of conduction electrons. In the case of this material, 400 of them effectively are attached to the F level. So the first thing that happens is when they start to interact, there's a hybridization, the mixing of the F level with the conduction levels. So as soon as there's mixing, you know gaps occur. Okay? And as soon as gaps occur, then resistivity changes and everything. And then when this very strong effect happens, the effective mass goes way up with low temperatures. That's if you have one impurity. If you have more impurities, so I already explained that the strength of this interaction increases. And increases to a point here where there's a phase transition and you cannot describe it using perturbative calculations. That's when it becomes the most interesting. So it's equivalent to quarks. So here's the effect on the resistivity of one electron, one impurity. So the resistivity just increases and saturates at a quite high level. This is the resistivity of a quantum dot. So it's really very, very strongly interacting. And then when you have, so as far as the electronic structure is concerned, so if you have just one, there's a resonance between the F level and the conduction electrons, and you get a very strong peak at the Fermi energy. So this gives you a very high density of states. It gives you, it's very narrow, it means there's no dispersion, so that means it's a very heavy mass. But once you put many F electrons inside, they start to communicate with each other. Once the electrons scatter here, at lower temperatures it makes them communicate with one another by the RKKY interaction. So when that happens at low temperatures, then all of these F electrons are connected to one another, and the conduction electrons, and so a gap appears in the spectrum. And this gap hybridizes the F levels and the conduction electrons, and then eventually the resistivity drops again. So if you have just one impurity, it saturates. As you increase the number of impurities, it goes up and then comes down. It becomes metallic at very low temperatures. Okay. So here's a picture from the density of states, or the dispersion band structure. So in the density of states, you get a peak gap, and then these very heavy electrons appear just at the Fermi level. In the dispersion, what happens is that this conduction band here and the F level, which doesn't disperse, is just sitting there. Eventually they mix and you form a gap. And so you now have a very heavy occupied state here. And that tells you that the Fermi surface should change shape, because the number of electrons now is different. The F level becomes part of the conduction electron structure. So we should see a change in the Fermi surface. So we're looking at this material, cerium-2 rhodium indium-8, which has a nice property of being fairly two-dimensional. So this is the material. So blue is cerium, then there's indium. There's different kinds of indium according to how many ceriums are coordinated to. These are coordinated to 4 ceriums. These are coordinated to 2 ceriums and 2 rhodiums, and those also. And that's coordinated to just 2 ceriums. So there's lots of atoms per unit cell, but we should be able to distinguish them. So this is the resistivity. So you see that at the beginning it's a metal. The resistivity is dropping with temperature, like all metals. Okay, and then it reaches a minimum as the F electron starts to, the individual F electrons start to interact with the conduction electrons. Okay, the F electrons are still not talking to each other. It's just conduction electrons interacting with just individual F electrons. The interaction is not too strong. But once you lower the temperature, the interaction gets stronger and stronger and stronger, and the resistivity shoots up. And then at lower temperatures, all of the F levels become, they start to talk to each other, everything talks to each other, becomes coherent, and the resistivity drops dramatically. It becomes a very, very good metal. This part, I'm not so sure I understand. So I'm just repeating what some theorists say. So why does it become a very good metal is a question. The idea is the following, that if you have all these F levels, and they're now talking to each other, correlated with each other, and with the conduction electron, the idea is that the conduction electron starts to move freely around the lattice like a wave, and the resistivity just drops and it's metallic. But somehow my intuition doesn't understand this. So we need to measure this. We haven't measured that yet. But there are many interesting things to see. So this is the Fermi surface of this material when we measure it at 1 photon energy, okay? And so this is the calculation from the LDA. And the agreement is pretty much zero, unfortunately, because the F level, you cannot put it in ad hoc. If you put it in just in a regular calculation, it will be, how do you adjust the interaction between them? It's very difficult to do. So people just put it in, try to change the energy and see when it agrees the best. But it's very hard to do, and it doesn't really seem to work very well. But fortunately, theorists have developed newer ideas, the dynamical mean field theory, coupled with LDA. So it has all of the features of the LDA, but you treat the interaction of F electron with a conduction electron as a small cluster, which you put in the lattice later, and you see that the band structure is, some things are similar, but it has a different structure, right? Different numbers. So there are two kinds of states here. The states here, the center of the zone, they're really three-dimensional light. But these states here are two-dimensional light. And we can tell that by changing the photon energy, because then we change Kz, the z part of momentum. But first let me show you, I only showed you the conduction electron Fermi surface. Here is the spectrum with the F level. Now the F level is totally non-dispersing at high temperatures. And this is the F0, okay? The F0 level is a very low energy, it doesn't do anything. And up here, right at the Fermi energy, or just above the Fermi energy, you have the resonance that occurs because of the interaction with the F level and the conduction electrons, but it's still not coherent. And then there's some spin orbit splitting. We're not too sure about that, but we're going to study that next. So this level is just above the Fermi energy, but its density of states is very high, and so we expect it to interact very hard, very strongly with conduction electron. We see more than one peak. This F7 halves and 2 halves, F1. This is the full F0 level. So that's what happens. So it's totally non-dispersing. It's like an isolated moment. It doesn't form part of the electronic structure. It just refuses to do that. And now we know that this is a three-dimensional material, so we can change the photon energy and we probe different parts of K, Z. And near the center of the zone, there's a lot of change because the bands are dispersing along the Z direction, but at the edges, it doesn't disperse very much. They're two-dimensional light. But we still need to plot this in more detail to get the full band structure. But that, of course, agrees with these calculations. You can see that this is at the top of the Brillouin zone. This is along gamma. So you have, different structures because of the dispersion. But what's more important is they also predict this very strong change in the volume of the Fermi surface and the shape. Because as you lower the temperature, if you go from high temperature to low temperatures, the F electron and the conduction electron start to interact, and then you have one more electron in your electron count, and you have to change the Fermi surface. So they predicted this already, and it's quite an interesting effect because this is beyond what you could do with most other theoretical understanding because, you know, there's no way to change the a priori from first principle, change the count of electrons in the system of different characters and their interaction. So this is the data, and you can see very dramatic effects. So this is at high temperatures. You see states that are just crossing the Fermi energy, this line here, and we can only see them a little bit above the chemical potential because of noise if we divide by the Fermi function. And then as we lower the temperature, you see the gap appears. And it appears because the conduction electrons are mixed with the F electrons. Okay? So now you should have a very heavy F electron right at the Fermi energy. We don't see it in this case because it's a wrong photon energy. We have to use a different photon energy. But we know it's there. And but they are very strongly interacting, the band structure change. You can see it in several parts of the beryllium zone. So really, there are very strong effects, and they occur. The surprise here is that this occurs much before the actual point where the Kondo resonance becomes very strong, or where there's coherence of the F electrons. It occurs at much higher temperatures, an order of magnitude higher. Here's another point in the beryllium zone. You can see, okay, this goes backwards. There's no gap here, and then all of a sudden there's a gap. The states just disappear above the Fermi energy. So things are doing more or less what they're supposed to do, but we have to find this F electron. It's not here, so we don't know where it is. We have to look for it, but that requires just more experimenting. These experiments we only did 1 or 2 runs, so it's very short time. We obtained a lot of results. That's what happens when there are good students working in the machine. So there are lots of results, but we need to do some more critical ones to find out all the mysteries, to solve some of the questions that we need to solve. And here's what happens when you change the temperature. You see that there's a dramatic, where the states cross the Fermi energy, that defines the Fermi surface. This is the same cut in beryllium zone, and you can see, look at this dramatic change when you change the temperature, okay? And that would be also very difficult to account for normally, because obviously it's completely changing the symmetry of the system. So it's very, very exciting and interesting. So here's what happens. This is the Fermi surface at 20 Kelvin, okay? And if I go to room temperature where there's no interaction between the F electrons and the conduction electrons, look at that. I mean, this is incredible because it's well beyond any simple picture that you might have about the material. There's a complete change of, look at, this thing grows, it pushes these others away. Here they're well separated. There's lots of very interesting effects that we don't understand yet. But it's very exciting. I'm very happy to be able to work with people here. They make beautiful samples, and hopefully we will have some more to say in the near future. Thank you very much. Sure, I don't want to keep you away from coffee, and posters are more important. We want to see what the students are doing.
Perguntas? Está? Vamos agradecer ao professor mais uma vez.